Physics is the study of the universe. It explores the fundamental laws that govern everything around us. From the smallest particles to the largest galaxies, physics seeks to uncover the secrets of how the universe works. Two of the most profound and revolutionary theories in physics are quantum mechanics and the theory of relativity. These theories have transformed our understanding of space, time, gravity, and the nature of reality itself. Quantum mechanics governs the very small world, the world of atoms and subatomic particles. It reveals a strange and counterintuitive reality, where particles can exist in multiple states at once, where information can be transferred instantly, and where the act of observation can affect the outcome of an experiment. On the other hand, relativity deals with the very large, the world of stars, galaxies, and the universe as a whole. It shows us that space and time are not absolute but intertwined in a fabric called space-time, which can be warped and bent by massive objects. Together, quantum mechanics and relativity provide a framework for understanding the universe from the smallest to the largest scales. They have led to groundbreaking technologies like lasers, transistors, and the Global Positioning System, GPS, and continue to inspire new generations of scientists to explore the frontiers of knowledge. In the early 1900s, physicists started exploring the atom, the basic building block of matter. They discovered that atoms aren't tiny, unbreakable balls as previously thought. Instead, they're made of even smaller particles like electrons, protons, and neutrons. The behavior of these particles is governed by the laws of quantum mechanics, a strange and wonderful set of rules that challenge our everyday understanding. One of the main ideas in quantum mechanics is wave-particle duality. This idea says that particles like electrons and photons can act like both waves and particles. This means that, depending on how you observe them, these particles can act like tiny balls of matter or like ripples spreading across a pond. Another key concept in quantum mechanics is quantization. This means that energy, momentum, and other physical quantities can only exist at specific, discrete values, like steps on a ladder. This is very different from classical physics, where these quantities are thought to change continuously. Quantum mechanics also introduces the concept of probability and uncertainty. Unlike classical physics, where the future can be predicted with certainty, quantum mechanics tells us that we can only calculate the probability of certain outcomes happening. One of the most mind-boggling aspects of quantum mechanics is the idea of superposition. This principle states that a quantum particle can exist in multiple states at once until it is observed. This means, for example, that an electron can be in multiple places at once, or a photon can have multiple polarizations at the same time. A famous thought experiment that illustrates superposition is Schrödinger's cat. Imagine a cat trapped inside a box. Inside the box, there's a device with a 50% chance of releasing a deadly poison. Until we open the box, there's no way to know if the cat is alive or dead. According to quantum mechanics, the cat is in a superposition of both states, alive and dead, until we make the observation. This thought experiment highlights the strangeness of the quantum world. It suggests that the act of observing somehow causes the superposition to collapse, forcing the particle or system to choose one state or the other. Quantum superposition isn't just a theoretical curiosity. It has real-world implications and is being harnessed in various technologies. For example, quantum computers, which have the potential to revolutionize fields like medicine, materials, science, and artificial intelligence, rely heavily on the principle of superposition. Another strange thing in quantum mechanics is entanglement. Entanglement happens when two or more particles become linked, even when separated by huge distances. These entangled particles share a special bond, and their fates are intertwined. Measuring the state of one entangled particle instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has puzzled and intrigued scientists for decades. Imagine two entangled photons, one sent to Aliyah and the other to Bilal, who are light years apart. If Aliyah measures the polarization of her photon and finds it vertical, she instantly knows that Bilal's photon will have horizontal polarization, even though there's no time for information to travel between them at the speed of light. Quantum entanglement has profound implications for our understanding of reality. It suggests that there may be deeper connections in the universe than we previously thought, and challenges our intuitive notions of space and causality. Entanglement isn't just a theoretical concept either. it has practical applications in emerging technologies like quantum cryptography and quantum communication, where the secure transmission of information is crucial. Part 5. The Theory of Relativity, a new understanding of space and time. In the early 20th century, Albert Einstein revolutionized our understanding of space, time, and gravity with his theory of relativity. Einstein's theory comes in two flavors: special relativity and general relativity. Special relativity, published in 1905, deals with the relationship between space and time. It postulates that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This seemingly simple assumption has mind-blowing consequences. It implies that time is not absolute. Instead, time is relative, meaning it flows at different rates for observers moving relative to each other. This phenomenon is known as time dilation. Special relativity also shows that the mass of an object is not constant but increases with its speed. As an object approaches the speed of light, its mass approaches infinity, making it impossible to accelerate to the speed of light. Section 6. Time dilation. Time is not what we think it is. Time dilation is one of the most exciting predictions of special relativity. It states that time passes more slowly for moving objects relative to a stationary observer. The faster an object moves, the slower time passes for it. For example, imagine a clock on a spaceship traveling at close to the speed of light. From the perspective of an observer on Earth, the clock on the spaceship will appear to tick slower than a similar clock on Earth. This is not an illusion. Time really does pass slower for the clock on the spaceship. Time dilation has been experimentally verified many times, using atomic clocks placed on airplanes and satellites. The results of these experiments confirm the predictions of special relativity with remarkable accuracy. Time dilation is not just a strange scientific phenomenon. It has practical implications for technologies that rely on precise timekeeping, such as GPS satellites, which need to account for the effects of time dilation to maintain their accuracy. Section 7. Bending spacetime. Gravity's cosmic dance. In 1915, Einstein published his theory of general relativity, which expanded special relativity to include gravity. General relativity describes gravity not as a force, but as a result of the curvature of spacetime. According to Einstein, massive objects warp the fabric of spacetime around them, just like a bowling ball placed on a trampoline warps the surface of the trampoline. This curvature of spacetime affects the motion of objects nearby. Objects moving near a massive body follow curved paths, not because they are pulled by a force, but because they are following the curvature of spacetime itself. General relativity has been experimentally verified through many observations, including the bending of starlight around the sun during a solar eclipse and the gravitational redshift of light escaping from massive objects. Section 8. The interplay of quantum mechanics and relativity. Quantum mechanics and the theory of relativity are two of the most successful theories in physics. However, they seem to disagree with each other. Quantum mechanics describes the world of very small things where energy and momentum are in tiny amounts, and particles can exist in multiple states at once. On the other hand, relativity describes the world of very large things, where gravity warps the fabric of space-time. Attempts to combine these two theories have faced big challenges. One of the main hurdles is that general relativity describes gravity as a smooth, continuous curvature of space-time, while quantum mechanics describes the universe as grainy and probabilistic in nature. Despite these challenges, the search for a unified theory, often called quantum gravity, is one of the most active areas of research in theoretical physics. Part 9. Conclusion. The enduring quest to unravel the secrets of the universe. Quantum mechanics and the theory of relativity have revolutionized our understanding of the universe. They have revealed to us a world stranger, more wonderful and more interconnected than we ever imagined. These theories have led to groundbreaking technologies and continue to inspire new generations of scientists to explore the boundaries of knowledge. Our journey through the quantum world and the vast expanse of space-time is a testament to the power of human curiosity and our relentless pursuit to understand the universe and our place within it. The quest to unravel the secrets of the universe continues, driven by the same sense of wonder that led our ancestors to look up at the stars and contemplate the vastness of existence.